In the previous video, I introduced you to the idea of the buoyant force, and we examined the buoyant force which would act on a cylinder which is immersed in a liquid. As it turned out, it wasn't that hard to get an expression for the buoyancy force acting on a cylinder immersed in a liquid. But in this video, we're going to try looking at a different shape, namely a sphere. So in this figure here, I have a picture of an iron sphere, which is completely immersed in some liquid of constant density. And we're going to assume that the iron sphere is denser than whatever liquid it is immersed in. So we have this string over here to hold up the iron sphere so that it does not sink to the bottom of the liquid. Anyway, what I'm going to do now is come into the figure and draw in squiggly arrows to illustrate the effect of the surrounding fluid pressure on the iron. As in the previous video, the pressure will always act perpendicular to whatever surface it's pushing on, and also the pressure will increase as we go deeper into the liquid. So right here at the top of the iron sphere, that's where the pressure would be weakest, and also it would be pushing downward on the top of the iron sphere. Now, as I go around the side of the iron sphere, the pressure is going to become stronger as we go deeper, and also the direction of the pressure is going to change so that the pressure is always pushing perpendicular to the surface of the sphere. So let's go down around the right side. And as I go down around the right side, the strength of the pressure increases and the direction changes as well. And now I have the strongest pressure pushing up on the bottom. Now I'm going to go up the other side. And as I go up the other side, the pressure is going to get weaker. And also change direction because the direction of the surface is changing. Now, starting from this figure, how would we determine the buoyancy force acting on the iron sphere? That looks like a pretty hard problem because the strength and direction of the pressure force changes continuously as we go around the surface of the iron. If we were going to calculate the net force that the pressure exerts on the iron sphere using a direct method, that would require third semester calculus, and even then, it would be a pretty ugly calculation. But maybe we don't have to do that. Maybe there's a trick we can use so that we don't actually have to use methods from calculus 3 to figure out the net force that the pressure exerts on the iron. Here's what we're going to do. We're going to imagine that we have a blob of the exact same liquid which is surrounding the iron sphere. Moreover, we're going to imagine that this blob has the exact same size and shape as the iron sphere itself. We're going to call this blob the displaced fluid. We call this the displaced fluid because this is the fluid which would be occupying this space if the iron sphere were not there. So here's what we're going to do. We're going to imagine that we can grab that iron sphere and pull it out of the liquid really fast, leaving a hole behind. And into that hole that was left behind when we extracted the iron sphere, we're going to slap in the displaced fluid. So now let's draw another figure which illustrates the situation after we have taken the iron out and substituted back in the displaced fluid. Okay, in this figure, I have removed the iron and substituted with it a blob of the surrounding liquid with the exact same size and shape as the piece of iron. Let's first ask ourselves, what would be the effect of the surrounding pressure on this blob of displaced fluid that we swapped back in? Well, we can start by drawing in squiggly arrows to represent pressure pushing down on the top. Then we go around the sides, and as we go around the sides, the strength of the pressure increases and the direction in which the pressure acts changes as well. Now look at the two figures here and here. In each of these figures, the buoyancy force would be the net force exerted on that thing by the pressure in the surrounding liquid. Now, first of all, can you tell that the buoyancy force in either one of these situations would point upward? We can tell that the buoyancy force would point upward because as we look at the figure, we can see that the surrounding pressure gives just as much rightward force as it gives leftward force. However, the upward components of the pushes are stronger than the downward components of the pushes. So in either figure, we have a buoyancy force pointing upward. Next question. In which of these scenarios would that upward buoyancy force be stronger? Can you see that these two buoyancy forces are equally strong? The reason these two buoyancy forces are equally strong is because the action of the surrounding pressure on the iron sphere and the action of the surrounding pressure on that displaced fluid that we swap back in are exactly the same. The pressure in the surrounding fluid doesn't care what it's pushing on. The pressure in the surrounding fluid is only reacting to the size and shape of the object, not what the object is made of. So the two buoyancy forces both point in the same direction upward and are exactly as strong as each other. So what I'm going to do here is come in and make a big equal sign to show that these two buoyancy forces are actually equal to each other. Now I would like to concentrate on this second figure showing the displaced fluid. Other than the buoyancy force, are there any other forces acting on that blob of displaced fluid? Well, we would, of course, have the gravitational force. So I'm going to come in and draw a vector representing the gravitational force. In fact, that blob of fluid only has two force vectors acting on it, the buoyancy force and the gravitational force. Now, which would be stronger, the buoyancy force or the gravitational force? Well, ask yourself this question. Suppose you had a swimming pool, and somewhere in that swimming pool, you had a blob of water which was exactly the same as all the other water in that swimming pool. Would that blob of water, which was exactly the same as all the other water in the swimming pool, would that blob of water sink to the bottom or would it rise to the top? Neither, right? That blob of water, which is exactly the same as all the other water in the swimming pool, would just stay there. What allows it to just stay there? Well, it must be the case that the buoyancy force and the gravitational force are equally strong as each other. So I'm going to put in a funky equal sign here to indicate that the buoyancy force and the gravitational force are not exactly equal to each other, but they are equally strong. Let's put this all together. When we started the video, we were trying to figure out the buoyancy force that the surrounding liquid would exert on that piece of iron immersed in the liquid. We have now shown that the buoyancy force on the piece of iron is exactly equal to what the buoyancy force would be on a blob of the displaced fluid swapped back into the position of the iron. But we have also shown that that buoyancy force that would act on the displaced fluid is equally strong to the gravitational force that would act on the displaced fluid. Let's put it all together now. That buoyancy force on the piece of iron must be equal to the weight of the displaced fluid. Let me say that again. The buoyancy force acting on an object immersed in a fluid must be equally strong to the weight of the fluid that that object is displacing. Let me write that out. So we have shown in this video that the buoyant force, or in other words, the net force exerted on an object by the pressure of the surrounding fluid, is equal to the weight of the fluid that that object is displacing. This is known as Archimedes' principle. So if we actually had an object immersed in a fluid and we wanted to figure out the force that the surrounding fluid exerts on that object, you don't have to take third semester calculus. All you have to do is find a blob of the displaced fluid with the same size and shape as that object, weigh that blob, and the weight of that blob is the strength of the buoyant force on the object. In the next couple of videos, we're going to be doing a couple of example problems using this principle.